Life Sciences Lecture 3, The Scientific Method. So what are we looking at in this lecture? Let's see if I can get this slide to go. There we go. Here are our objectives. Define the scientific method in its 5 parts, which are the formulation of a question, hypothesis, prediction, testing, and analysis. Give the necessary components and examples of each of the 5 parts. And our other objective is describe the parts of a research paper. So we start out in this lecture with a quote from Galileo, our good friend that we got to know in the last lecture. In questions of science, the authority of thousands is not worth the humble reasoning of a single individual. So what does Galileo mean by that? He means that it doesn't matter how many people hold an opinion if it's not backed by sound reasoning and logic. So, a single humble individual can have their opinion based on research or based on logic or based on science, and that actually means a lot versus what everybody might believe if it's not really backed by anything. So we know that Galileo was very much into research and into setting experiments up in such a way that they would be repeatable by anybody at any time. So he's a great one to get some wisdom from as far as research goes. And research has a lot to do with what we're talking about today, which is the scientific method. So before we dive into what the scientific method is, let's kind of summarize a little bit what we've gotten out of the last 2 lectures. So I don't think this is supposed to say what we learned from our scientific past. It's supposed to say what have we learned from our scientific past. So if we, so in the notes, there's a list of things that I came up with. You might be able to come up with, a similarly long list of other things that we've learned from our scientific past. But here are a few things that I see that are important, that were important to scientists in the past and are still important to scientists today. And we can see those ideas pulling through all the way from ancient Greece to labs around the world today. And that is asking questions, right? We're not going to get answers if we don't ask questions. And who felt like learning something or asking questions was the best path to learning something? That was Socrates. So Socrates taught us that asking questions of ourselves helps us to understand what we already know and helps us to understand what we know and what we don't know. So asking questions is really important, and it's only by asking questions that we find out what we know and what we don't know. And if we don't know, then we can come up with some ways to try to find out what we don't know. What else is important? Eliminating what we know not to be true to drive us toward the truth. So again, the Socratic method is a method of questions that what we're doing with it very often is peeling away. It's like making that marble statue. It's peeling away what is not the form that you want, or it's asking questions to remove what you know not to be true, and hopefully in the end it reveals what is true. Now remember, of course, in science, that we can never, ever prove something to be true. We can disprove something. We can create an experiment and find out that something is not true, but we can never know that something is definitely true. We can only accumulate evidence that might uphold a theory, but we can't prove that a theory is true. So eliminating what is not true is the key to getting as close as we possibly can, or as close as we can in the moment, to what is true. Also in the past, empirical evidence was very important to scientists. Evidence being able to be stated or represented by numbers. So a couple bullets down from there in the notes. Logic and mathematics were very important to scientists, starting with the sophists and, all the way up to current time. Like when Copernicus, who was not in current time, but when Copernicus said, hey, you know what? I think actually that the sun is the center of the solar system. He could say that all he wanted, but once he could say it with numbers, then it was more difficult to deny than if you just said it with words. So logic and mathematics are a key part of science and scientific research. The bullet in between there, separating oneself from what we think the answer will be so that we can see what the answer really is from an unbiased perspective. That's not easy. And that's a task that scientists deal with all the time, is you go into something and you think you know how it works. That's why you're setting up your research to prove something, which of course we have to keep in mind that we can never, ever, ever prove something to be true. You can know in your heart of hearts that acupuncture works, but how are you going to prove it? All you can do is do experiment after experiment after experiment to indicate that using acupuncture or using a certain point or using a point protocol or whatever is more effective than placebo, is more effective than no treatment, is more effective than some other treatment, but you can't prove necessarily that it works, or that it is the thing that is getting those results. But the more experiments that are created around that, the more that we support, the more supportive evidence there is that indicates that that the theory that acupuncture works, or whatever the theory is, that it potentially might be true. So anyway, separating oneself from what we think is a difficult thing, but it's a necessary thing in science. And so, which is why we use logic and mathematics, so we can kind of turn information into numbers, and have it be this very, logical thing, or numbers, or something, like numbers that we can use logic with. What else? Observation of the world around us was very important, back in, Aristotelian physics, even though now nobody teaches Aristotelian physics, he came up with his ideas by observing the world around him. And as did Newton, and as did Einstein. These are three very big names in physics through time. And how did they come up with their ideas? By observing the world around them. And even, especially in the case of Newton and Einstein, observing the world around them from outside of their vantage point. Within their mind, they had to observe things from outside their vantage point of the reality that they are living in. So also not such an easy task. Building on the previous work of others is important. We're going to see that show up in the scientific method. Sharing information is important. We saw Galileo create experiments and share his results. Copernicus shared his results, and Galileo supported his results, and got himself on house arrest for that. But sharing information is so important, so that we're not just all starting from scratch, but we're building on the people who came before us and continuing to build and continuing to build. In Chinese medicine, we'll often say, or researchers will say, that they've gotten to where they are by standing on the shoulders of giants. So our predecessors, the people who came before us, the people who did the work that led up to our work, that those people are very important, and we wouldn't be where we are without that work that came before us. Carefully constructing and recording experiments so they can be replicated by others. We saw Galileo doing that. And examining and questioning one's own beliefs if they don't fit with the evidence. So again, that's kind of back to that idea of trying to separate yourself from your beliefs, making the evidence empirical so that you can kind of hold it outside yourself and examine, hopefully in an unbiased way, what you're looking at. Okay, so let's see, what is the scientific method? So here we have a flow chart of the scientific method, but let's go ahead and define this first. So scientific method is a body of techniques for investigating phenomena, acquiring new knowledge, or correcting and integrating previous knowledge. To be termed scientific, a method of inquiry must be based on empirical and measurable evidence subject to specific principles of reasoning. Okay, so in that definition of scientific method, we see a whole lot of those ideas that we've been talking about, that we've been seeing by looking at the past. We see that we want to be able to use reason, logic. We want things to be empirical and measurable. So, we want to turn things into numbers as much as we can. We want things and we're going to use the scientific method to investigate. So we're going to observe the world around us, observe things and go, what's that? Why does that happen like that? And ask questions and try to figure those things out. So we'll be either acquiring new knowledge, or also another key thing that we do in research is we look at the research of lots of other people and get that together and make our own conclusions based on other people's research. So anyway, that's what the scientific method is. It is a body of techniques for investigating phenomena, acquiring new knowledge, or correcting and integrating previous knowledge. And then to be termed scientific, a method of inquiry must be based on empirical and measurable evidence subject to specific principles of reasoning. So there are 5 parts of the scientific method, although we see more than 5 parts here on this flow chart. But that's okay, because one of these parts is sort of a subcategory of another part. So our first part of the scientific method is the formulation of a question. So on our flow chart, we see the red box on the top, ask a question. That's the first part. So the question can refer to the explanation of a specific observation. So maybe we observe that the sky is blue, and then our question is, why is the sky blue? Or anything that we can observe, we can ask a question about it. The question can be open-ended, like, is this true or is that true? Or so the example here in the notes, does sound travel faster in air than in water? So, so it's there's a definite answer there. It's going to be one or the other, or it might turn out that it's the same in both, that there isn't a difference. But that's an open-ended question. Or how can I design a drug to cure this particular disease, which is a very open-ended question, because that's not necessarily an easy thing to do. So part of this process of formulating a question involves looking up and evaluating previous evidence. So we're doing that background research. Actually, you know what? Let me. I have slides for each of these things. Let me zoom through the flow chart here, and then we'll go back and talk about each of these things a little bit more. So just look at the flow chart. The first one is the formulation of a question. That's asking a question. Part of that is doing the background research. So we need to know what questions people have asked in the past and what evidence has been accumulated on that topic already. And that will help us to form the question. So you see the arrow goes both ways between ask a question and do background research, because your asking your question has to be based on your background research. You might have a question, but then when you go do that background research, you very well might need to change that question based on the evidence that you found. But once you have formulated a clear question, your next step of the scientific method is to construct a hypothesis. So a hypothesis is your best guess about what the answer to your question is. And then you're going to test your hypothesis with an experiment, and then you're going to see if that worked or not. And if so, then you'll go on and analyze your data and draw some conclusions. If not, then you're going through that troubleshooting route of trying to fine-tune the experiment so that the procedure that you're doing does work, or that you can change the procedure to something that does work. But once you have a procedure that's working and you're getting information, then you're going to analyze that information and draw some conclusions. And so the conclusions that you're going to draw either align with your hypothesis, or partially align with your hypothesis, or do not align with your hypothesis. And then based on that, then also you will communicate your results, but based on the results that you get, then that informs future research. So it informs your next hypothesis. So you'll always end with a where do we go from here based on this information. Okay, so asking a question, constructing a hypothesis. Let's see, what is the next? I'm going to say it the way you have it in the notes here. Asking a question, constructing a hypothesis, making a prediction about what you think will happen, testing your hypothesis, and then analysis of the data. Those are the 5 parts of the scientific method. Okay, so let's go through them one at a time though here. So formulation of a question. So like I was saying, formulation of a question can be open-ended, or can be just sort of referring to an explanation of a specific observation. But always formulation of a question is based on previous evidence. So this is where we're, standing on the shoulders of giants, where, where all of the research that has happened already and the huge body of knowledge we might already have about a topic, that's what we have to start from. So we need to understand that body of knowledge the best that we can first, so that informs our question-making process. Okay, so the next step is coming up with a hypothesis. So a hypothesis is a conjecture. It's a statement about, based on the knowledge that you have. It's a statement about what you think is going to happen. So let's see, in the notes, a hypothesis is a conjecture based on the knowledge obtained while looking at previous evidence in the process of formulating a question. So again, creating your hypothesis is also informed by that back research that you're doing. So on the slides, these things you see in the slides, these are called books. And this is how research used to be done. That's a joke. Okay, so we can still look up things in books, and actually, when we're studying Chinese medicine and looking things up, we do our research in books quite a lot. But but nowadays we most journals are online. If we're reading scientific journals, mostly we're looking up stuff online very often. Anyway, that's the next step: formulation of a question. We're going to look up and evaluate previous evidence. I'm on hypothesis. Okay, here we go. So hypothesis is your conjecture. This is what you think is going to happen. So what we see on this slide is you had your what they're calling a problem, but that's your question. And your hypothesis is what you think the answer is. And so there are some possibilities. What this slide is showing is that either this shows H0 versus H1. So hypothesis 0, or maybe that means the hypothesis doesn't hold up, does not explain, does not answer the question, or the hypothesis does answer the question, where it does stand up once we have done our research. So anyway, the hypothesis is what we think is going to happen. So it might be very specific. So in the notes we see a specific hypothesis. The example is Francis Crick's DNA makes RNA makes protein. So Watson and Crick are the researchers who are given credit for discovering the shape of DNA, the double helix shape of DNA, and other things about DNA as well. And so this is Francis Crick's hypothesis that DNA molecules, the cells use DNA molecules to construct RNA molecules, and the cells then go on to use RNA molecules to construct protein. And so that's his hypothesis, and there would be actually many steps to proving that hypothesis. But Watson and Crick, this is just Francis Crick, but the two of them together, Watson and Crick, who came up with the shape of DNA, all of that research that they did was based on other people's research. They were not in the lab for that. They were in the library. So, based on other people's research, they were able to accumulate a lot of information and come up with their best guess about the shape of DNA. And now we have microscopes strong enough to back up their prediction. Okay, so what else about a hypothesis? A hypothesis might be broad, so such as unknown species of life dwell in the unexplored depths of the oceans. So we're not saying something really specific. We're not saying there is a specific species that has 3 eyes and 4 horns and it lives in the unexplored depths of the oceans. We're just saying unknown species, things we haven't seen before, live in places where we haven't explored, okay? So that's a hypothesis, and we could test that hypothesis by going to those unexplored depths of the ocean, or sending something down that can go there and collecting data and see if we find unknown species in the waters living there. A statistical hypothesis is a conjecture about some population. For example, the population might be people with a particular disease. The conjecture might be that a new drug will cure the disease in some of those people. And so with a statistical hypothesis, we want to see a certain percentage of of change in the population that we're looking at. So and this is the kind of thing that could be used, like if we're doing research around acupuncture, that we would see more than half of the population with back pain show marked improvement in their back pain with regular, weekly acupuncture for 6 weeks, or something like that. So, we have a population that's people with back pain, and we could be more specific. We could be men with back pain, men over 60 with back pain, or we could say pregnant women with back pain. So we have our population, and then we're going to say, a certain statistical hypothesis is going to say what percentage of that people or more might we expect to see an improvement in that pain or something like that. So terms commonly associated with statistical hypotheses are null hypothesis and alternative hypothesis. So a null hypothesis is the conjecture that the statistical hypothesis is false. So we would expect to see X percentage of people improving. And then if we don't see that, then that would kind of say that hypothesis is not true. So that would disprove that hypothesis, which actually, again, in doing scientific research, disproving something is more certain than proving it because we can't prove it. So oftentimes we'll pose a null hypothesis because that's a clear thing that we can say, this does not work. That we can say, we can disprove something. So if we have a null hypothesis, let me see, researchers normally want to show that the null hypothesis is false. And so, because we're using that to say, this is not how this thing works. So an alternative hypothesis is the desired outcome. For example, that the drug does better than chance or placebo. So, so then the alternative hypothesis would be, if a certain percentage of people do get better with using this drug or using this procedure, that would be our alternative hypothesis, that this thing does work, or that, whatever, perhaps it works. So that's a null hypothesis, an alternative hypothesis. And so keep in mind, I've been mentioning this all along. A scientific hypothesis must be falsifiable, meaning that one can identify a possible outcome of an experiment that conflicts with predictions deduced from the hypothesis. Otherwise, it cannot be meaningfully tested. So when we're coming up with a hypothesis, it has to be testable and it has to be falsifiable. We can't design a study around something where we can't, where no matter what the evidence is, that doesn't give us evidence that what we're testing isn't true, if that makes sense. So it has to be falsifiable. All right, the third part of the scientific method is a prediction. So on the slide we have, if A, then XYZ. So if this thing works, or if this is true, then we would expect to see XYZ. So the presence of XYZ is what is going to indicate to us that A is happening or is accurate or whatever. And then the flip side of that, if not A, then not XYZ. And so which those things say the exact same thing. So if we don't get XYZ, then A is not what's happening there. So that's this is a basic logic statement here, and this is what we're doing with the prediction. So in the prediction, we're determining the logical consequences of the hypothesis. So again, we need to set this up in a way that where we can say, here's our question, here's our hypothesis, and now. And if our hypothesis is accurate, if this is what's happening or what is, true-ish, even though we can't prove it's true, then these are the results we would expect to see, right? That's what the prediction is. And then we go about our research seeing if those results are indeed what we see. So let's see, what else about a prediction? The less likely that the prediction would be correct, simply by coincidence, the stronger evidence it would be if the predictions were fulfilled. So we want good, strong evidence that this thing that we said would happen really, truly did happen. And that, this is, in research, you see this all the time, especially with drug research, where they're going to tweak numbers the best they can to show that the control group that got the new drug did better than the placebo group. Or better than the no treatment group. And sometimes it's by the tiniest little hair of a percentage, but they try to make it as, this is research being done by drug companies who they want to show that their drug is working. In a case like that, that's really weak evidence that the drug has anything to do with those people getting better. But if we had really strong evidence, what we would see is 80 or 90 or close to 100% of the control group who was getting that treatment would be better as a result. That would be much stronger evidence if we saw numbers like that. Ideally, the prediction must also distinguish the hypothesis from likely alternatives. So we need to be able to distinguish the hypothesis that this thing that we're testing worked. We need to distinguish that from placebo, or just distinguish that from just the natural course of things or something like that. So we need to be able to account for all those things. So there are a lot of things that, designing a scientific research is, scientists take painstaking care to make sure that all of these steps are done correctly, and and everything is said correctly, and everything, so that in the end, so that you have good results. The next step is testing. So we've asked our question, we've come up with what we think the answer is. So we posed a question, we came up with a hypothesis, we have made a prediction about what we think will happen. So if our hypothesis is true, then XYZ should be the outcome. If our hypothesis is not true, then we would expect not to see XYZ. So we're going to set up our experiment ever so precisely, and run it. And that's what the testing is running our experiment. And we'll do it over and over and over again. The more evidence that we get, the stronger it upholds our hypothesis. And so this is, again, when putting together a study, we want to be sure that we're putting it together in a way that anybody could take this information and recreate this study and get the same results. So the next piece that we're looking at here in this lecture is a scientific paper, which is like taking this work that's done and then publishing it. So when you're looking at this in a paper, you want to have in a paper all of the specific information about what tools you used, what methods you used, everything, so that anybody could reproduce it. And because them reproducing your work is just going to help to uphold your hypothesis. Okay, so testing. So this is an investigation of whether the real world behaves as predicted by the hypothesis. And sometimes that's not what happens. Sometimes we have a hypothesis and then we test it and we go, oh, look at that. That totally did not work even in the slightest. Here's an example of taking it to acupuncture research. So one of the things that's difficult with researching acupuncture is having a placebo or having a control group. So you can always have a control group where no treatment was done, but having a control group where some kind of treatment like acupuncture was done, but it wasn't real acupuncture, so that's usually referred to as sham acupuncture. So how do you do sham acupuncture without it working? That's kind of a difficult part when you're working on putting together research in acupuncture. And so, but sometimes we get weird results, unexpected results, I should say, that then drive research in another direction that reveals a whole other something that we didn't know. So, for instance, in doing so this, I don't remember what it's called, but there was a method of like having a needle over a point, but the needle wasn't actually either just very barely in the skin, or it wasn't in the skin at all, or the needle was in deeply. So in a particular study, they were setting it up where so that the patients didn't know if the needles were in or not, but they had needles, say they were testing a protocol, prescription of points that was like the same points on all the people that were being tested, and let's say it was for back pain or something. So they had a handful of points that they were using, and it was the same points on everyone. But even the people who were in the control groups, they still had needles like in a little contraption over the points. And so some people in one control group had those needles over points, but the needles were not in the skin. One control group had the needles over points and the needles were barely in the skin. And then one control group had the needles over the points, or the test group had the needles over the points, and the needles were at the depth that the researchers meant to have the depth at to be testing their hypothesis. Well, what they found when they analyzed their evidence was that the people with the needles in just barely, that control group, they ended up getting better results than the people with the needles in as deep as the researchers felt like they should be. And specifically, I think it was the people with the chronic pain, the longer lasting pain, or the pain that had been going on longer leading up to the research, with that very shallow insertion, they got better results than the deeper insertion. And so researchers had to scratch their head and say, wow, so there's something here with this shallow insertion and chronic pain. And so then that started a whole nother chain of events as far as researching the difference between shallow insertion and deep insertion, treating chronic pain and treating acute pain. So anyway, so sometimes things don't go the way we think that they will, and sometimes we learn from that, and that's all good. And it's so much better to learn from that rather than to tweak the results, which we see that happening all the time, of course, rather than tweaking the results to show the, evidence that we thought it was going to be. We don't want that. We want to be clear and empirical and logical and all that, at least in the world of science. All right, so testing, what else? Okay, so we do our testing. If the results that we get agree with our hypothesis, then confidence in the hypothesis increases. Sorry, my dog is barking here. He has something to say because someone's walking in the door. Shh, 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 shh. If the results conflict with the hypothesis, then the confidence in the hypothesis decreases. And agreement, and this is again coming back to that idea that we can never prove something to be true, agreement with the hypothesis, so the results turning out the way that we think they will, that does not assure that the hypothesis is true. Okay, if everything went exactly the way we think it did, that doesn't mean it's true. That just means that we haven't disproven it yet. But the more evidence that we get, the stronger that hypothesis stands. But future experiments may reveal problems in your testing method or in your hypothesis or in your assumptions or something. Experiments should be designed to minimize possible errors. So especially when we're doing tests with people, we need to do double-blind tests so what a double-blind test is where neither the subjects nor the researchers know who is in what group. The irony of that is, so double-blind tests are ones in which the subjects, neither the subjects nor the researchers know who is receiving what treatment. And so here's where I was going with that, where the irony of that is part of what the need for that shows us is the power of the mind, that placebos are amazingly powerful, and thinking that you're getting the treatment that you're sure is going to cure you, that puts you on the road to recovery. So we try to accommodate for that kind of thing by running double-blind tests. Okay, so failure of an experiment does not necessarily mean the hypothesis is false. The failure could be due to faulty equipment, faulty conditions, maybe the test wasn't set up as well as it could be or whatever. What else? Most individual experiments address highly specific topics for reasons of practicality. So it's easier to answer one tiny specific question than it is to answer really big, broad questions. And very often big, broad questions are asked initially in a line of research, but then as we get those answers, then we refine and refine and refine, and we ask more and more specific questions. Let's see. And then our last step here is analysis. So analysis involves determining what the results of the experiment show and deciding on the next actions to take. So again, so then this is where we are taking our data, putting it into pie charts, putting it into bar graphs, putting it, looking at it, crunching those numbers every different way so we can really accurately analyze the information that we have and see what those numbers are telling us. And we do the best that we can when we're analyzing those numbers to let go of what we expect and try to just see what those numbers are actually indicating. And it's difficult to do. And, I wouldn't want to be a researcher because all of this is difficult to do, I think, although a lot of people are super excited about it, and bless them because we need research happening. All right, what else? The predictions of the hypothesis are compared to those of the null hypothesis to determine which is better able to explain the data. If the evidence has falsified the hypothesis, a new hypothesis is required. So one of the things we always see is at the end of a paper or the end of the presentation of material is the what's next step. Like, this is what we did, this is what we thought would happen, this is what did happen, and so then what does that tell us? And then where do we go from here? And so that's kind of what some of this is saying. If the experiment supports the hypothesis, but the evidence is not strong enough for high confidence, then other predictions from the hypothesis must be tested. So we need more information to build confidence in that hypothesis before we can kind of make any strong statement about it. And once a hypothesis is strongly supported by evidence, a new question can be asked to provide further insight on that same topic. And so you can see here that this would continually, we would be refining and refining the questions that we ask the more that research continues in a certain direction. So this model of the scientific method underlies the scientific revolution. So everything, and the scientific revolution, what underlies that is what was happening in ancient Greece. So this is our lineage and our heritage as Western scientists. That the things that were important to the ancient Greeks, those things were also important to the scientists of the scientific revolution or during the Renaissance, and post-Renaissance as well, right up to modern day. So let's see what else it says here. 1,000 years ago, scientists demonstrated the importance of forming questions and subsequently testing them. And, that was happening then, is happening still today. And so when that's happening today, what happens next is we publish our research. So in the real world, what happens is first we have to come up with the research that we want to do, then we have to get funding for it. So that's a whole lot of what researchers do, is write grants or apply for grants, I should say, and try to get funding for their research. And so people who head labs like that, the main person at a lab, one of their main jobs is funding the whole thing, finding funding for the research that they're doing. So anyway, but then the idea is that we're going to publish this research. So let's just take a brief look here at the parts of a scientific research paper. Now you guys will be reading research papers through the course of being in school. Most of the research you're going to be reading is about acupuncture. And that's great. And what's interesting is testing acupuncture through these Western research means is new in the world of acupuncture. I mean, it's been happening for quite some time, but considering the span of acupuncture, it's a very new thing in the world of acupuncture. And so, but that's an important thing because a lot of what's happening is this process of bringing to light the efficacy of acupuncture so that conventional Western practitioners can begin to understand what acupuncture can do, how it works, what it treats, and that kind of thing. So it's kind of looking for some legitimacy in the eyes of conventional Western doctors and other scientists. So anyway, so it's important that acupuncture research be being done. So what are we going to see when we read a paper? So the first thing we'll see in a paper is the abstract. Oh my gosh. There we go. So the abstract is a complete overview of the paper in a short paragraph. So if you need to do some research, or you just need to write a paper on something, you might read a number of abstracts to find enough studies that have been done about the topic that you're writing about. So the abstract, so a research paper is totally different than like a newspaper article or or like reading a novel or something like that. If you're reading a novel, you don't want to know how it ends in the very beginning, although sometimes you do, but that's like a teaser and it pulls you through to the end. But this is different. An abstract does tell you the whole story. It tells you what they were asking. It tells you how they went about. It tells you what the hypothesis is. It tells you how they went about testing it, and tells you what the results are. But the reason the abstract is a key part of the paper is a couple of things. One is it's a brief overview. So when you're looking at a lot of papers, all you're doing is reading the abstracts. And that is so much faster than reading the entire paper for everything. And so you're actually never going to read the entire paper until after you read the abstract and you find out that there is material there that benefits your research. Then you'll go in and read the whole paper. And the other thing is that when papers are in a journal, especially online, you can read the abstracts for free, but then often you'll need to pay to read the entire paper, unless you already, if you get subscribed to the journal, then you can read the whole paper. But if you don't subscribe to it and you're just looking for information because you're doing some research for a paper you're writing or something, you can read all the abstracts you want for free. But you're going to have to pay if you want to read the whole paper, most likely. There are free papers though too. Okay, so abstract is the first part. The next part is the introduction. So the introduction basically speaks to the research that the scientists did leading up to the question that they're asking. So it tells you about other people who've done research along the lines of this research that they've done and that they're writing about. It tells you the results of that other research. It basically summarizes the work of everybody leading up to this work that is in this paper. So the introduction kind of speaks to both, to a few parts of the scientific method, posing the question, but also the research that was behind coming up with that question, but also the hypothesis. And so we should find all of those things in the introduction to the paper. And then methods. The methods, let me say this too, that there is research where you are doing experiments, and there is research where you are basically just reading literature. And so those papers actually are going to be put together a little bit differently. But basically the same format is followed. Anyway, it's just going to, in the methods section, if somebody is compiling other people's research, then the methods section has stuff like, these were the search words that we use to find the data, or to find papers, and this was and like that kind of thing. Like, how did they do that? How did they do that research, when all it was reading papers, versus how did somebody carry out an experiment or carry out a study that they designed? So so methods might look really different depending on what kind of research is being done. So if the research was, we did auricular acupuncture on pregnant women with back pain, we use these points. The methods are going to include all of those things, like what points they use, how do we, what do we call those points? How do we find those points? What's the location of them? How deep do we put in needles? How long do we leave them? How do we assess whether or not it worked? Like, so basically usually with that, we're having patients say, like, on a scale from 1 to 10 or a scale from 1 to 5, what's their pain level going into it? And then, and then what's their pain level over the course of the weeks of the treatment? And then at the end, what's their pain level? So all of those things are things that we would see in the methods part of a research paper. Like, how did they do it? And, if this is like straight up Western, like say we're doing genetic research, then it's things like, we took these cells, we spun them down, or we took, whatever. We spun cells in a, what's it called? You know what I mean? The thing that spins, that separates out things of different weight. And then we extracted from that, a certain amount of stuff. We put it in a spectrometer, so we could see what different colors were in there, that kind of stuff. That you have to be in a lab and have all those tools and, all of that. But that, that's totally research that's done. Okay. That's the methods section. So the methods section basically tells you about your testing, tells you exactly how that testing happened, and the methods section is very important so that somebody else can come along and replicate your testing. The results then, that matches up with the analysis part of the scientific method. So the results, that is the presentation of your calculations. It's your tables, it's your graphs, it's your statistical analysis of the data. So, a certain percentage of the population got better, or we had this population that we were testing, this percentage of them dropped out through the course of the experiment and didn't complete it. This percentage got better, this percentage got worse, this percentage had no change. Those sorts of things are the kinds of results, the kinds of things we might see in results. And but then also we'll like turn those results, and this is the kind of thing that like statisticians do, where we'll turn those results into things like, so using this, well, no, I guess that would come in the discussions and conclusions, but we also want to like turn things into like not just a certain percentage of the people got better, but then what does that mean? Like that somebody would have an X number, like they're 10 times more likely to improve if they do this, or like that kind of thing. So still using numbers to say, here were the results that we got. The next part of a paper is the discussion and conclusions. So the results are just your tables. These were the numbers. This is what we got. The discussion is, what do those results mean? What can we conclude from that? And then that also takes you to that, where do we go from here? What's the next step? So what would be the next question to ask based on this? And that, essentially drives future research. That's the discussion and conclusion part. And then the very last part of a scientific research paper is a list of all the literature used and cited in the research. So basically that goes back to that back research that you did, which is also, this is a part of the paper that nobody ever reads. You never read a paper from, front to back and read all of that. But if that paper had good information for you for research that you're doing, you might go in and look at their sources and then go back to those sources and look at their research, because that might also be helpful for you. So the literature cited is also an important thing. So, okay, so gosh, that took longer than I thought it was going to take. I thought this was going to be a shorter lecture. Anyway, so here were our objectives. We defined the scientific method in its 5 parts. So we talked about the formulation of a question. We talked about a hypothesis. We talked about what a prediction is. We talked about the testing part of things and analysis. And we gave the necessary components and examples of each of the 5 parts, and then we took that stuff and said, where does that turn up in a research paper? So we described the parts of a research paper, and hopefully we got that and made those connections about where each of those parts of the scientific method shows up in a research paper. Your homework for this lecture is to define each of the 5 parts of the scientific method, and then you're going to email me your responses. So that's it for lecture 3. So what's up next is next week In class, for our live meeting, we'll be talking about physics. We'll be defining the different fields of physics, and then you'll have lots of videos to watch. And then actually, after all of those videos, you will also have a video. We'll start diving into chemistry actually next week as well. Okie dokie. I hope it was enlightening, and I will see you in class next week.